Okay, so let's continue here with chapter 5 and get to the part that I really love to talk about, which is Mars. Look at it, just a fascinating world, so many interesting features, and let's get right to it then. Okay, of course, Mars is the Roman god of war. Certainly, you would think because of the color of Mars, the color of red, you think anger, you think blood, and so ancients saw that reddish color in the sky and naturally came up with the god of war. Kind of makes sense. And that would be Ares for the Greeks and Mars for the Romans. And of course, our scientific interest in Mars is all about the fact that it is the most Earth-like planet in our solar system. And we know that Mars used to have water. The number one thing that we look for when we look for life is water. And Mars had plenty of liquid water on its surface long ago. So we're quite interested in that, whether it still has life or even if it had life at one point. Either way, that would be a tremendous discovery. All right, let's look at the big picture of Mars here. We've reached the final terrestrial planet, the last planet that you can walk on that has land. It has a larger eccentricity. In other words, its orbit is more oval than, let's say, Venus or Venus or Earth. Our orbit is much more circular. None of the orbits are actually, none of them are circulars. They're all circles. They're all ellipses. But Mars is particularly stretched out. So we say it has a large eccentricity, which we'll see in just a moment. And because it is more eccentric, look at that range. It goes from about 1.38, the distance that Earth is from the sun, to 1.67. That's actually a really big difference. And so in terms of the sunlight, if you remember, the intensity depends on the inverse square law. So a little change in distance is actually a big change in the intensity of the sunlight, 45% different. When it's at perihelion, in other words, at its farthest point from the sun, or excuse me, at its closest point, perihelion, to its farthest point, aphelion, 45% difference. That's huge. That's a big deal. We don't have that situation on Earth. Our distance is almost the same all year round, so that doesn't affect our seasons. Our seasons are caused by our tilt. Mars is tilted as well, but it has that extra factor built in, the eccentric orbit. Okay, so we finally have a planet, unlike Mercury and Venus, that can be on the other side of Earth from the sun. We can see it far from the sun. That means we can see it late at night. We can see it high in the sky, which is great for viewing it. And every 2 years, roughly, the sun, Earth, and Mars line up. We say that it's at opposition. It's on the opposite side of us from the sun. And you'll notice that that's when we send spacecraft to Mars. Just about every 2 years, like clockwork, we send a spacecraft there, which is really cool, and that's why. Okay, so at its closest, 0.37 AUs from the Earth. That's from Earth to Mars. And of course, if we ever send people, that's when we would go, when it's at opposition. Okay, here you can see in the green circle, if you'll see that, that's Earth's orbit around the sun, which is very, very circular. Now look at the distance over here. On the right-hand side, you see, and especially the bottom right, where at that opposition, when it's Sun, Earth, and Mars they're going to be particularly close together. So all oppositions aren't created equally. Yes, every 2 years, Earth and Mars pass each other, but different ones are closer than others. So you have another opposition here where it's Sun, Earth, Mars, and there's a bigger gap if you look at the top left there between them during that opposition. It's still the best time to go there, but it is different because of the elliptical nature, the more elliptical nature of Mars's orbit. And don't forget, going back to, I guess, chapter 2, was it, when we talked about this, the fact that if you follow Mars night after night, it's drifting one way through a constellation, and suddenly, for a couple months, it will actually appear to drift backwards in the sky. And that's what drove ancient people crazy trying to figure that out. We call that retrograde motion. But we know it's just simply a result of the Earth passing Mars. So every couple years when we pass Mars, for a couple months, it will appear to drift backwards, kind of like passing a big truck on the highway, and it looks like it's going backwards in your window, even though you know it's actually going forward. And that's what Copernicus That's why he brought back the heliocentric theory, really to be able to explain that in a way that made a lot more sense than how Ptolemy was trying to explain it in ancient times. Okay. Now, we just got through talking about Venus, which is incredibly bright in the sky. Now we get to a planet that is not bright again. Let's talk about why. First of all, of course, it's farther from the sun than Venus. And according to the inverse square law, if it is twice as far away, it's only going to receive 1/4 the brightness, 1/4 the intensity of light as that's compared to Venus. Okay, so it's only receiving 25% of the light to begin with, roughly. Then you have this fact. A lot of people don't realize this. Mars is small. It's quite a bit smaller than Venus and Earth. I like to call Venus our twin sister and Mars our little brother. So only 30% of the surface area, and unlike Venus, it's dark. So Venus had those white reflective clouds, and Mars has this dark, ruddy surface, which is only 15% comparable to Mercury, let's say, in reflectivity, or albedo it's called. Anyway, despite all of that, every 2 years, Mars does get pretty bright in the sky, and it can actually be brighter than the brightest star by a little bit. So I always love that. I love when Mars is bright and it has that orange color, and it really stands out and is beautiful in the sky. Now, what gives it that famous color of it? Well, iron oxide. Mars has rusted over. I mentioned that it had water on its surface, and that water oxidized and became iron oxide. And that gives it its famous tint. All right, so that gives you some idea. Obviously, Mars is not red. We call it the red planet, but it's the color of rust, kind of a brown, kind of a red. It's the color of rust, whatever you want to call that. And here we see some of these giant, beautiful features that we're going to talk about later in the chapter. I can't wait. All right. Well, I think that's enough for this section. We'll do the other section next time. Thanks for listening.